Alright, 9.4 video notes. Today we're talking about the area of quadrilaterals. So we spent the last section or two talking about properties of parallelograms and rectangles and squares and rhombuses and trapezoids and kites and everybody else. So now we got to go through and try to figure out how do we find the area of each of those shapes. So I'm going to give you some definitions, but then I'm going to also try to show you where they come from. So you might be able to derive them even if you can't memorize it. So let's kind of start off with the nice thing about the formula for parallelograms, which also works for rectangles, also works for squares, also works for rhombuses. So those four big ones at the bottom of the hierarchy, they are all just base times height. So area is the base times the height, or BH for short. Now, so rectangles, that's pretty standard. You have a rectangle, this would be your base, this would be your height. All right. Squares, same type of deal. Sometimes you will see formulas that are written as S and S, and they say the area of a square is side squared. It's the same thing. It's base times height. Just the two numbers are the exact same on a square. So you can view it that way. On a parallelogram, the base is either one of these two. Okay, there's a top base and there's a bottom base. They're both B. And the height is the distance between the bases. Okay, so your height, your H, is the distance between the bases, and you must see that little perpendicular mark. If you don't see that, then it's not a true height. So A is not even involved in the area formula. It doesn't matter what A is. It's the base and the height. And basically why that works is because you could cut off this little triangle right over here. You could just take some scissors and just cut that right off, and if you slid it over and moved it, it would fit perfectly right over here, and then you'd be right back to a rectangle. So that's why a parallelogram and a rectangle have the same area formulas, because you can cut it and shift it over, translate it, and you're right back to a rectangle. Now, there is an alternate formula for a rhombus that I think is often easier. Because of the fact, we talked about this in the properties, but because of the fact that these two diagonals, they're 90 degrees and they bisect the corners, basically you have four triangles that are congruent inside there. And if you found the area of one of those triangles and multiplied it by 4, basically what's going to happen is you are going to have a formula that's 1/2 diagonal number 1 times diagonal number 2, which is, they're calling it P and Q. I have never really seen it written that way in too many books. Normally I see it written like this. But it's 1/2 diagonal times diagonal. So we'll do a couple of those coming up here in a second. Moving on down, we go into the trapezoid, which is probably the most complicated formula out there, because it's kind of like a rectangle in a parallelogram. The problem is, in a parallelogram and in a rectangle, the two bases are the same. So you kind of have this top base and you have this bottom base. All right, and this particular diagram is calling it A and B. I've seen some books call this base number 1 and base number 2. But the problem is, if I use the top base, it's too small. You know, if I just use base 1 and multiply it times the height, I'm only finding the area for this little square right here. All right, so that's too little. It's not big enough. But then if I actually use the bottom base and I multiply it by the height, now I have too much. Now I have a rectangle that's too big. Well, what you'll find is the amount that you're too large, this extra triangle here and this extra triangle here, is exactly the same as this piece and this piece. So we're exactly have too much, twice as much as we really want to have. So how I think of the area of a trapezoid, it's not the top base, it's not the bottom base, it is the average base times the height. All right, the average base. And how do you find the average base? Well, you add those two up and you chop it in half. And then you take that number and you multiply it by the height. And there's a lot of different ways or formulas to write this. Some books say 1/2, add the two bases times the height. If you like that formula, fine. If instead of using 1/2, you'd rather just divide by 2, that's okay. So remember what the average base really is. The average base has a name. It's actually called the median. So if I can find the middle of these two lines, boom, this is the average of the bases, aka the median. All right, so now when you multiply that number by this number, you're in good shape. So we'll do a couple of those coming up here too. I'm just going to say that a kite is the same as a rhombus. The kite has the same formula as a rhombus. Now if you wanted to, you could find the area of this big triangle and double it, and then find the area of this triangle and double it, and find all four separately. Or you can just do the 1/2 diagonal times diagonal. You know, so in this case, Q is this diagonal, P is this diagonal, so 1/2 PQ. Or this bottom one, P times Q divided by 2. They all kind of do the same thing. All right, so let's put all this into play and let's get after some questions here. Find the area of each parallelogram. So I know the formula for parallelogram. It's just base times height. Excuse me. So there's my base. There is my height. So base times height is the area. So we are looking at area is 14 times 3, or 42. And whenever you're doing area, the units are squared, okay, because we're technically counting up how many little squares make up that shape. If this was on the coordinate grid, I could count blocks, and that represents area. So on this next one, it looks like we have 9 by 5, so that would be 45 square meters, meters squared. This one they try to trip me up and they put some extra numbers in here, but ultimately again it's base times height. 10 times 8 would be 80 square inches. So those are pretty straightforward with parallelograms. Now we do have a few down here that get a little bit more challenging. So if you look at this problem here, number 4, I see a base is 10 and this is the other base, but there's no height in there. So I can't do it going that way. So what you kind of have to visualize is you have to visualize if I turn this thing the other way and stood it up long ways like this, and this was the 8 was up top and the 10 was on the side, all right, and my 12 actually is cutting across. All right, so my 12 is connecting this 8 with this 8 right there. So that is the height between those two bases there, which is 12. And I honestly think this is an impossible picture because 10 is the hypotenuse and there's no way that the hypotenuse can be bigger than a leg of the triangle. So this is a bad question by the computer generator, the textbook that I stole this from. But either way, I do area of a parallelogram is base, which is 8, times height, so that would be 96 square millimeters, or 96 millimeters squared. Now on number 5, alright, so on number 5, this one's a little bit different. I do have the base, and since it's a parallelogram, the top and the bottom have to match. So my base is 2.5. My height is actually outside the parallelogram. So the height between the two bases, and I'm always looking for that perpendicular line, is out there. So it's 4.8. So 48 times 4.8 times 2.5 would be 48 quarters. That'd be 12. So 12. And another way to write this would be square inches. Okay, if you like that way you can, but usually it's kind of written like that as shorthand. Number 6, same thing, base times height, 7.5 times 2, 15 meters squared. All right, now let's move on down, take a look at some of these ones. In a parallelogram, a base and its corresponding height are in a ratio of 5 to 3. The area is 135. So this one I actually have to work backwards. Notice that they give me the answer. They tell me what the area is. So I'm going to set up my parallelogram. I'm going to draw a picture. And this is my base. And this is my height. And I know when I multiply base times height, I get an answer of 135. But I got to find two numbers that are in the correct ratio of 5 and 3. Okay, so this is, it says the base to height ratio. So this represents the B, this represents the H. Now I know 5 times 3 doesn't come out to be 135, so I have to find what magnification power it is. So I'm going to actually use like what we did earlier and use those extended ratios kind of things. So the base is 5 times some number, the height is 3 times some number. So 5x times 3x is 135. Now if your algebra is not very good, right now you could just kind of start trying numbers. You could say, well, if it's in ratio from 5 to 3, we could try 10 to 6. That would be the same ratio. We could multiply our top row by 3 and be 15 times 9. We could multiply the top row by 4. And so these are all ratios that are basically, mess that last one up, that's actually a 12. But these are all parallelograms that have the correct 5 to 3 ratio. And looking through the list, the only pair I think that comes out to equal 135 would be this pair right here. That comes out to be 135. Now, if you really like the algebra, you could have kept going here and had 15x squared is 135. Divide both sides, and you'd have x squared equals, what's that, 9? And so x ends up being 3. And then when you plug it in over here, you would get 3 times 3, which was 9, and then you would have 5 times 3, which was the 15. So your x basically finds your multiplier here, what you multiply the original ratio by. Alright, so now we're down here into the practice, and we have some trapezoids on here, and it looks like we get into kites. So I'm going to keep on going because we really didn't get to do in the notes up there, I didn't see many trapezoids or other stuff, so I'm going to try to do one of each shape just so you have a little bit of practice. So on number 1 it says find the area of the trapezoid. So I have to remember the trapezoid is the average base times the height. Now sometimes you can just look at it and you kind of know the middle number. Other times to find the average of the bases, I would add up the two bases and chop it in half, and that is your average base, and then you can multiply it by the height. So for instance, on number 1, this base is too big, this base is too small. It's kind of like the 3 little bears. I got to find the base that's just right. So I'm going to average those two. I'm going to go 9 plus 16 and chop it in half. So that's 25 divided by 2. So 12.5 is this average base in here. All right, 12.5. And visually, it looks like it's about halfway between 9 and 16. It looks right. And then I'm going to multiply that average base by the height, and I get 125 feet squared. So that would be the area of the trapezoid there. So I'm going to let you fight with number 2 and number 3 for practice, and you can use number 1 as an example. Let's go down, find the area of these trapezoids. Now these ones are a little bit tougher, and I'm going to kind of leave these up to you, but I'm going to give you a few hints along the way that might help you out. So for instance, this is your first base, this is your second base, so you are going to have to find the average, which that shouldn't be a big deal. The problem to this one is you're going to have to figure out the height. So I'm going to give you some hints. To find the height, you may need the Pythagorean Theorem. You're probably going to have to use some a squared, b squared, c squared type of stuff. And I'm going to get you kind of started on this. If you look at this picture and you look at what's going on here, I see that this top is 8 and this bottom is 18. So I should be able to transfer this 8 down to the bottom, which then tells me that this piece over here is 10. You know, the whole thing's 18, but I think just this piece is 10. And since this piece is 11, you could solve that little triangle using the Pythagorean Theorem to find out what h is. So that's a little hint that's going to get you through 6, 7, and 8. You're going to have to do some Pythagorean Theorem work to find some of these heights. Looks like over here you may be able to do some special right triangle stuff to find the height, or Pythagorean Theorem maybe. Moving on down into the practice, we have a bunch of kites and we have a bunch of rhombuses, so this section isn't too bad. Kites and rhombuses have the same formula. It's 1/2 times diagonal number 1 times diagonal number 2. So let's just pick, I'll do the first one for you and I'll let you battle through these. So 1/2, well, diagonal 1 is right here. It's 2 plus 6.5 for a grand total of 8.5. So that's the red diagonal. Now if I do the other one maybe here in purple, 4 plus 4, that would be 8. And you crank that out. Half of 8 is 4. 4 times 8.5 is 34 square feet. Okay. Now, if you didn't know the area of a kite, another way would be to find each triangle separately and put them all together. So for instance, this green triangle right here, all right, has a base of 2 and a height of 4. I know the area of a triangle. It's 1/2 base times height. So 1/2 of 4 times 2. Well, half of 4 times 2, that's 4. So I know that this little triangle has an area of 4. So this triangle has an area of 4 because they're congruent. Well, then I move over to this other piece, and if I do this triangle over here, well, that triangle is 1/2 base times height, which comes out to be 13. So now I know that this triangle is 13, this triangle is 13, and I believe when you add up all 4 of those triangles, 4 plus 4 plus 13 plus 13, you will get 26, 8, you will get 34. So you can see they match. It's just a lot more work to find the 4 triangles separately than it is to use the diagonal theorem. So I would definitely use the product of the diagonals. I think it's easier. Now, some of these problems, you're missing some pieces, and I'm going to give you a hint, Pythagorean Theorem. If you're ever missing some pieces on these, the Pythagorean Theorem is probably going to be needed. And one thing to know about diagonals and rhombuses, a hint here is that the diagonals are always 90 degrees or perpendicular. So you're always going to use Pythagorean Theorem on rhombuses and kites. Let's see if there's anything else. 20, we've already done the trapezoid. Some more trapezoids. So some things on a coordinate grid. I believe we've pretty much hit every shape. Now there's some challenging problems in there, but I've at least done an example of each of the shapes. So hopefully these notes were short and you can be ready to rock and roll in the practice tomorrow. See you.